do that here. Concentrated acetic acid contains approximately 96% by mass. The density of acetic acid is 1.05 grams per mil. The solvent is water, so 99% of the time the solvent will be water. What is the molality of the concentrated hydrochloric acid? Okay, so what is molality? Okay, it's moles of solute over what? Kilograms of solvent. Okay, in this class, the solvent will always, 99% of the time, be water. 99% of the time, the solvent will be water. So our solute here is going to be acetic acid. Okay, this is sometimes called concentrated acetic acid. Just for your reference, is also known as glacial acetic acid. Okay, 96% by mass. Okay, what does that mean, 96% by mass? Okay, this is also known as mass percent. Okay, mass percent. All right, so this is the same thing. If I were to deconvolute this, if I were to break this 96% by mass, it essentially means this. It essentially means 96 grams of acetic acid divided by 96 grams of acetic acid. Okay, plus how many grams of solvent water? Because the denominator is the whole thing, solute and solvent. So if this were an exam and you got 96%, okay, how much did you miss? It's 100 points. So yeah, 4 grams, right? 4 grams of water. We'll use, I'll write distilled water. So I think this is fairly straightforward now, I think. 4 grams is the same thing as, okay, to convert it to kilograms, this is kilograms of solvent. To convert it to kilograms, you're going to move the decimal place 3 to the left. Kilograms. Okay. And then solute moles is going to be acetic acid. Let's go ahead and convert this 96 grams of acetic acid to moles of acetic acid. Okay, 1 mole of acetic acid contains how many grams of acetic acid? Okay, carbon is about 12.01. Hydrogen is about 1.01, but we have 3, right, Antoinette? Yes, ma'am, 3. Plus carbon is another 12.01. Plus oxygen is 16.01 times 2. Yes, ma'am. Plus 1.01. So it's about 60.08 grams. Okay, the grams cancel. 96 divided by 60.08. Divided by 60.08, 1.598 moles, something like that. You guys getting that? 1.598 moles. Yeah. And we'll put that over here. And I believe it should be fairly linear from here. So the molality is moles of solute, which is 1.598 moles. Divided by 0.004 kilograms. And what is that going to be? About 400 molal. 400 molal. So this is the answer. This is kind of a trick question because you don't need to use the density. Okay, now if they ask you to convert this molal to molar, what would you need? You would need the density, that's correct. So this is a little bit of a trick question. Molarity to molality, or vice versa, you'll need the density. So just letting you know. But yeah, that's kind of don't need it. You don't need the density, okay? Make sure you know that. Same thing on the exam, just kind of a different number. You're going to follow the same pipeline. All right, are there any questions on the computation? All right, there's some extra credit computation, so I'm not going to go over it, but in case if you want some extra credit, there's going to be a osmotic pressure problem, pi equals mRT. So I will not go over it. But if you know how to do that, you know, some good extra credit for the test. Also the heating and cooling of water. Heating water from some temperature, let's say, I don't know, minus 50 degrees to 110 degrees C. Okay. So I'm not going to go over that because that's extra credit. Yes, sir.
You still provide formulas?
Yes, I will provide the formula and the constant. Yes, for this. And then here I'll give you all the the constants. Okay, the formula for this is Q equals ms delta T. Okay, without going over this and saving some time, how would you go about doing this? Okay, heating water. Let's say we heat 20 grams of water. Okay, without actually going over it, how would we do this or go about solving this problem? Okay, what do we start with? Okay, minus 50 to 0 degrees. Here we will use Q equals ms delta T. Okay, and we're going to use the ice, the S specific heat of solid water. Okay, that's a constant that will be given. And then what happens at 0 degrees? Phase change. So here you will not use Q equals ms delta T. You're going to use delta H, what, fusion, right? Which is, I'll give you this, it's about 66,000 joules over mole. Okay? So you're not going to use this equation, right? All right, so that's phase change. I'll give you the constant, so. Okay, then what's next step? You're at 0, you're heating. So now you go from 0 to what? 100. Okay, here equals Q equals ms delta T. And here the constant is going to be the specific heat of liquid water. H2O solid. Okay, then what? What's next? What's next is a phase change at 100 degrees, right? Here you will not use Q equals ms delta T, but you will use the delta H VAP, or vaporization, and this is, I'll give you this number, 40,700 joules per mole. And then finally, we go from 100 to our final destination temperature. In this problem, it will be 110 degrees. So here you will use Q equals ms delta T, and then you're going to use the specific heat of water as a gas or steam or whatever. Yeah, gas. Okay, I'll give you those constants. So this is how you go about doing this. You're going to add Q1, phase change Q2, Q3, Q4, Q5. Okay, add them up together, and you'll get how much heat is required. Okay, required to go from minus 50 to 110. Okay, when they say heat is required, what will be the sign of Q? Positive or negative? Required, not cooling, but required. Positive or negative? Very good. Okay, your Q is going to be positive. If it were cooling, what would Q be? Negative, because the heat is going to the universe or the surroundings. All right, so that's one computation if you choose to do it. All right, and then this is also another computation. Okay. And I'll give you that. R here is 0.0821 liters atmosphere per mole Kelvin. All right, some extra credit problems. I will not go over them, but you can use that to help boost up your grade. All right, let's go over some short answer questions, multiple choice for now. Let's do something that's very basic, okay, that I've been hitting hard with you guys, and that is concentration. Okay, there's two concentrations that we talked about that is used in chemistry. One is called molarity. So what are the units of that? Be specific. Don't just say moles. Okay, you'll say moles of what? Over solution. Okay, this is called molarity. Okay, we've been in Chem 1 labs. We just had one lab or two labs in Chem 2. Okay, anytime you work with a solution, what do you see? You see a big M there. Okay, that means moles over liter. Okay, remember, solution is solute plus solvent. The other one, this is known as molar. Okay, then we have molality, okay, which is moles of what over what? Over what? Of solvent. Okay, moles of solute over kilograms of solvent. Very good. All right, so that should be a gimme. Here's another gimme. The four colligative properties. This is something that we kind of hit home a lot. If you add a solute to a solvent and it totally dissolves, four things happen. Okay, what are those four things? Okay, we had a problem on it on Tuesday. Go ahead, Antoinette. The freezing point decreases. Okay, Okay, but I think this is next week's lab, if I'm not mistaken. What else happens? The boiling point increases because now you have solute and solvent that you got to overcome to get this to boil, so that's more IMF. What happens to the vapor pressure? It decreases because now you have solute and solvent, so that's more IMF to overcome, so it's harder to become a vapor. And then what else happens? Okay, if you have a semi-permeable membrane, okay, you'll establish what's called osmotic pressure. And that's the fourth colligative property. So these are called colligative properties. Okay, no matter what the solute is, this will always happen. All right, what are the three properties of a liquid? We talked about this. Okay, all liquids have this, not just water. Okay, this is water. Over there is ethanol. Okay, any type of liquid that you see in a lab, whether it's organic or inorganic, what are the three properties that it has? Almost universal. Okay, adhesion. Okay, so the molecule will stick to the glass, or yeah. Cohesion. Okay, we can put this as the second property or bunch it in with the first one, cohesion. This is molecules sort of coming together, forming a meniscus. Okay, what's the second one? Okay, on the surface we have a little bit stronger IMF, so we have here surface tension. The last one is viscosity. Okay, viscousness, viscosity. Right, what is viscosity? It is something that's a resistance to flow. Okay, some things flow, some things don't flow so easily. One thing that we mentioned about viscosity, we want to look for OH groups. Okay, if the molecule is decorated with hydroxyl groups, if the molecule has a lot of hydroxyl groups, then it's very viscous. Okay, because the OH groups represents what type of potential? Hydrogen bonding potential. Okay, so. Means more viscous. Okay, and as Bailey mentioned, the OH groups give it more hydrogen bonding potential. So that's some short answer questions for you guys. Let's also talk about a couple of other things here in terms of short answer and multiple choice. Right? Are there any questions on this? All right, so this is, I would say, just memorization, good points to know, and good points to carry on well beyond this class. Any other questions? All right, let's go over some multiple choice portions of this exam. Okay, we have IMF. Okay, so IMF stands for intermolecular forces. What do you guys think is the strongest intermolecular force? Okay, ionic. Okay, so can you identify an ionic compound? Okay, what would an ionic compound be or look like? That's true, but it would be a metal which would have the positive charge. Non-metal would be the negative charge. So yes, that is ionic. This is the strongest. So name some examples of ionic compounds. Sodium chloride. Okay. Sodium hydroxide. Yes or no? Sodium hydroxide. Ionic. Sodium chloride. Okay, are these examples of ionic compounds? Yes or no? Okay, positive sodium, OH hydroxide. This is called the hydroxide ion. Okay. What else? Calcium chloride. Okay, any metal with a non-metal. What about sodium phosphate? Is that ionic? Yes or no? Okay. Anything that has a positive ion interacts with a negative ion. Phosphate is PO4 minus 3. Chloride is Cl minus. Chloride is Cl minus. Hydroxide is OH minus. So all of these are examples of ionic compounds. There's many more. There's thousands more, to be honest. But these will have the strongest intermolecular force. So if they have the strongest IMF, okay, what can we say? Well, anyways, let's just fill out this table. Boiling point. Okay, what is the next strongest? Both of these are called polar, but one polar is a little bit stronger than this polar. So what polar is that? Both are polar. What is this called? This is called hydrogen bonding. Okay, what do we look for hydrogen bonding? Okay, we're looking for three things here. Anywhere in the molecule, the hydrogen will have a polar attraction to an OH. The hydrogen will have a polar attraction to the NH. And the hydrogen will have a polar attraction to the fluorine. Anytime you look at and see these three, then that's hydrogen bonding. Okay. So this would be strong, the strongest, strong. Okay, what's next here after hydrogen bonding? It's polar or dipole. Okay, so and then what would be the weakest? Okay, the weakest is dispersion. Okay, what functional group should we associate with dispersion? Okay, nonpolar. Okay, we have molecules that are polar and we have molecules that are nonpolar, but what functional group? The alkanes, okay? The alkanes. So let's fill out this table. If ionic is the strongest, what would dispersion be? The weakest. Okay, what would the delta H of vaporization be for an ionic compound? The amount of energy required to vaporize 1 mole. Would it be high or low? This would be the highest. This would be the lowest. And then what would the boiling point be for an ionic compound? Okay, this would be the highest, and this would be the lowest. Okay. What about the vapor pressure? Okay, what would the vapor pressure be? What would the vapor pressure be for something that is ionic? Would it be high or low? Can it form a vapor? The sodium chloride form a vapor? Sodium hydroxide form a vapor? So would it be high or low? Lowest. And what would be the highest? I don't know if you remember from the lab, where the intermolecular forces lab. Okay, the pentane and the hexane they just evaporated like that, and your filter paper was dry. I saw some of your filter papers. It was dry when you soaked it in hexane and pentane. Okay, it turns into a vapor really fast. Okay, and if it turns into a vapor really fast, it also means it can exert a high vapor pressure. So molecules held by dispersion would have the highest or lowest delta H vaporization. Okay, dispersion would have the lowest delta H vaporization. It takes very little energy, very little joules to vaporize 1 mole. And what type of vapor pressure would it have? High or low? Dispersion would have the highest vapor pressure, right? Does this make sense? Okay, substance, right? I agree or disagree? Okay. Dispersion molecules like nonpolar or the alkanes would have low delta H vaporization. Takes low energy to vaporize them, and because it has a low delta H vaporization, it has low energy to vaporize them, they can exert a high vapor pressure. Okay, let's go to the other end of the spectrum, something that is something that has a high boiling point. Okay, what would a high boiling point be? Something that is ionic, or what else could have a high boiling point? Huh? What else could have a high boiling point? Hydrogen bonding. Hydrogen bonding. Okay, so what do we look for hydrogen bonding? OH, NH, and F. Okay, more OHs, what does that tell you? More hydrogen bonding. More NHs, more hydrogen bonding. Okay, so more fluorines, but more OH, more NH, more NH, more F, more fluorine, more OH, which is hydroxyl group. Okay, so the hydroxyl group. That means more hydrogen bonding potential, which means higher boiling points. I'm just essentially reiterating what's in this table. Okay. Any questions or comments about this? Okay, more hydrogen bonding potential. Okay, how about more dispersion? What are we looking for here? Okay, in our lab, which do you think had more dispersion, pentane or hexane? Pentane or hexane, which had more dispersion forces? Okay, which has more dispersion forces? Okay, so this has 5 carbons, and this has 6 carbons. Do we know the structure of pentane and hexane? Okay, these are hydrocarbons. So what would require more force to evaporate? Something that has 5 carbons or something that has 6 carbons? 6. Okay, so more dispersion forces would be with more carbons. Okay. For the alkanes. Hexane would have more dispersion. Okay. Even though they're both alkanes, hexane has more dispersion. Okay. Because it's bigger, heavier. So imagine trying to vaporize a hexane. Remember, the hexanes are going to have their own IMFs interacting, but you're trying to break apart 6 carbons versus trying to break apart IMF for 5 carbons. So breaking apart IMF for 6 carbons is going to be a little bit more. Because there's 6 carbons rather than 5 carbons, so hexane will have more dispersion forces. Okay, and I wrote here hydroxyl group. Hydroxyl group is OH. OH minus is hydroxide ion, like sodium hydroxide, calcium hydroxide, lithium hydroxide. But if we have an OH at the end of a molecule, if we have an OH at the end of a hydrocarbon, it's not an alkane, but what will it be? Alcohol. Okay. And what do we know about alcohols? What is their main intermolecular force? Hydrogen bonding. They also have a small intermolecular force, and that's called dispersion, but all molecules have dispersion. Okay, but I do not know if I mentioned this. All molecules will have dispersion, but what's the main intermolecular force for the alcohols? Hydrogen bonding. Okay, everything has dispersion because remember, what did we mention about dispersion? The key point here is that it's very transient and fleeting. Everybody has dispersion. Okay, it's just that the nonpolar molecules, the driving intermolecular force is dispersion. Here, the driving intermolecular force for the alcohols is hydrogen bonding. Okay, the driving intermolecular force for the ethers is dipole-dipole, okay? But there's also dispersion. That's the driving one, but this also has dispersion. We all have dispersion. Every molecule has dispersion, but it's not the driving intermolecular force because all these molecules have circulating electron clouds. Right? So if they say dispersion for an alcohol, okay, but if they say hydrogen bonding and dispersion, is that the right answer? Yes, because everything has dispersion. Okay, but what has the most of dispersion? And the driving intermolecular force with the most dispersion will be the alkanes and nonpolar molecules. Okay, nonpolar molecules have no net dipole moment. These polar molecules as well as hydrogen bonding have a net dipole moment. That means partial positive or partial negative. Okay, this has no net dipole moment. Okay. So do we know an example of a nonpolar molecule? Can you name one?
Of a nonpolar one?
Yes. That's not an alkane.
Benzene.
Go ahead.
Is it benzene?
Okay, benzene, good one. Yeah, nice. Okay, this is benzene. Anything else? Each of these represents a carbon, by the way. Okay, another one will be CCl4, okay, carbon tetrachloride. Even though chlorine is electronegative, or even CBr4, anything with symmetry. Anything with symmetry. Okay, even though they pull equally and cancel out each other, so this would also be nonpolar. Okay, so for benzene and carbon tetrachloride, carbon tetrabromide, carbon tetrafluoride, what is the main IMF? What's the main IMF for these guys? Dispersion. Dispersion, okay? So make sure you can identify a nonpolar molecule. I think you mentioned that, Maria. Make sure you know alcohols have hydrogen bonding as well as dispersion, but dispersion is just so minor. More OHs, more hydrogen bonding potential, higher boiling point, higher viscosity. Highest boiling point would be ionic compounds like sodium chloride, sodium hydroxide, calcium chloride. There's so many different ionic compounds. You're looking for a metal with a nonmetal. Let's do.
I don't know if you went through this already, but the difference between ionic dipole and then just dipole-dipole forces.
So these are dipole-dipole forces. Hydrogen bonding and polar, they have a net dipole moment. So these are dipole-dipole. This is dipole-dipole. This is dipole-dipole, but hydrogen bonding. Okay. An ion dipole is where you have a full brunt of the charge. An ion dipole would be something like a sodium ion in water. Okay, water is a dipole-dipole, and sodium is an ion. Okay, so ion has the full positive charge, or it will have the full negative charge, and then a polar molecule will have a partial positive or partial negative. That's ion dipole. Okay, this is why calcium ion is soluble in water. Okay, this is our Gatorade or whatever, those energy drinks, Gatorade. I only know Gatorade. But the calcium ion, also called electrolytes, they are soluble in water. How is that possible? Because water has a dipole-dipole, as you mentioned. A partial positive with a partial negative. So this is what you call an ion dipole, Maria. Okay? The positive calcium ion will interact with the partial negative of this oxygen. That's ion dipole. Whereas a dipole-dipole would be this partial positive interacting with a partial negative. One dipole attracted to the other dipole. Here, this is the dipole partial negative, delta negative, partial negative, delta negative, interacting with the full +2 charge. That's ion dipole. This is why water, being a dipole-dipole with hydrogen bonding potential, can solvate ions like sodium, hydroxide, calcium, nitrate. It can solvate them. That's ion dipole. The full charge of the ion with the partial charge of the molecule. Okay, that's ion dipole. Okay, where does ion dipole go in here? That's something that I don't really know. It can either ion dipole, depends on what's the ion. It can be here, it could be above dispersion. I really don't know because there's so many ions and there's so many polar molecules that could solvate. So yeah, just need to know ion dipole is a full ion with partial positive or partial negative. All right, let's one final thing here. Let's say we mentioned that solution is solute plus solvent, and we mentioned mass percent. So let's say I have, and then we talked about this. What if I have 5% mass percent glucose? Okay, by mass. Okay, what does that mean? Mass percent. It means what's our solute? Glucose. Okay, let's say it's aqueous. 5 grams of glucose over what? What's in our denominator? The whole thing. What is the whole thing here? Solution. And what are our parts of the solution? 5 grams of glucose plus, let's say it's aqueous. And how much water? How much? 95, yeah. That's what mass percent means. It's the same thing we did at the very beginning of the class with acetic acid. The acetic acid problem. Okay, mass percent just means the mass of the solute divided by the whole thing. The whole thing is solute and solvent. That's mass percent. Okay. Also, this sometimes it goes M over M because there's other concentrations like M over V or mass volume or something. But on the exam, mass percent is the mass of the solute divided by the mass of the whole thing. Okay. We will not do mass per volume, but that's also another concentration, mass per volume. This is just mass percent. All right, are there any questions or comments? I think that's pretty much the exam that we went over. So go over Tuesday's practice sheet. Go over today's notes, and I think we should be okay. Okay, there's a couple of extra credit problems in there as well that we went over. Okay. So what will happen? Yes, go ahead.
What is the normal condition?
Oh, yes, thank you. Normal means 1 atmosphere. I totally forgot about that. Thank you. Caroline? Is that true? Caroline. Normal means 1 atmosphere. Okay, so if the normal boiling point of water is 100 degrees C, the normal boiling point of water is 100 degrees C, what is the pressure? 1 atmosphere. Normal means 1 atmosphere. So we have something called normal boiling point, or you may see, I see normal boiling point. I don't know about normal freezing point, but maybe that's also in the literature. But that means the vapor pressure is 1 atmosphere, or the pressure is 1 atmosphere. That's what normal means. Okay, anything else that I think I may have missed? It's covering chapters 11 and 12. And then turn in your quiz, unless you want to make that your drop. And then turn in chapters 11 and 12. Homeworks 11 and 12. And if there is no other questions, have a good weekend. I'll see you on Tuesday.